human quest for clarity must begin and end with physics. Why? Because physics is the most foundational of all the sciences. Even our most important psychological experiences are mediated by and through our physical brains. Without physics, there's no philosophy, or consciousness, or economics, or anything else. At least not in this world. This basic fact that everything is hinged on physics is going to make the task of understanding ourselves extremely challenging, because physics is intimidating, and trying to make sense of its mysteries seems downright impossible. If we don't get our physics right, however, our social systems will continue to be built on bad or truncated ideas, and that's something we want to change. Given that physics is so foundational to all of the sciences and humanities, what we need is a theory of everything to situate ourselves intellectually, and that's exactly what you see on the screen, represented with consummate simplicity by the phi and psi symbols. We've borrowed these symbols from physicist Yakir Aharonov and his team of collaborators. We'll have a lot to say about their important work later. Crudely put, these two symbols represent past and future causes coming together to create what we experience as reality in the present. Before we ask anybody to take these symbols seriously, there's obviously a lot to unpack, and that's precisely what we're going to try to do for a general audience in this lecture. As you can see in the structure on the screen, our theory of everything is a theory of quantum gravity that rests on two pillars. One of them is known as the two-time picture of quantum mechanics, which is the pillar on the left, and the other is string theory, the pillar on the right. As we proceed, I'll explain why these pillars are key to unifying physics through quantum gravity, and I'll use the breakthrough to conjecture one of the most beautiful and consequential symmetries in the history of science. The symmetry I'm referring to is represented mathematically by the disk in the center of the structure, known as a ds-ds conformal disk. These are all big words if you aren't familiar with physics, but don't worry because the coming explanation is very simple. Let's not get too caught up with the terminology. The ideas are much more important than the technical jargon. Below the pillars are several additional conceptual foundations. They are holography, extra dimensions, entanglement, and uncertainty. At the very bottom of the diagram, you'll see that our proposed theory builds upon the foundational work of the biggest names in physics. In other words, we're not starting from scratch here. We're building on a well-established scientific project that's been in the works for 500 years, and we're going to be meticulous about respecting and following the rules of this project. We'll proceed through this lecture in 5 parts. First, we'll introduce 3 foundational principles that will guide us in the development of our theory. Second, we'll explain what most physicists consider to be the main problem in contemporary theoretical physics. Third, we'll propose the solution to this problem. Fourth, we'll run through a thought experiment. Lastly, we'll talk about the possible ways to test our theory. So the first of our 3 foundational principles deals with the role of interpretation in physics. According to Nobel Prize winner Richard Feynman, when 2 ideas in physics are mathematically equivalent and lead to the same predictions, good physicists keep both interpretations in their head because they never know which one is going to lead to the next big breakthrough. Let's hear it from Feynman himself.
Suppose you have 2 theories, A and B, which look completely different psychologically, different ideas in them and so on, but that all the consequences that are computed are exactly the same. Suppose we have 2 such theories, how are we going to decide which one is right? No way, not by science. However, for psychological reasons, in order to get new theories, these 2 things are very far from equivalent, because one gives a man different ideas than the other. By putting the theory in a certain kind of framework, you get an idea what to change. And every theoretical physicist that's any good knows 6 or 7 different theoretical representations for exactly the same physics, and knows that that they're all equivalent, but he keeps them in his head hoping that they'll give him different ideas for guesses.
What Feynman is saying is simple. Interpretation and how we tell stories matters in physics. Foundational principle number 2 is a long-standing joke among physicists. The joke goes like this. There's a farmer with cows that aren't producing milk, so the farmer goes to a physicist for help. The physicist does her thing with calculations and whatnot, then tells the farmer, I have a solution, but we have to assume your cows are spheres. Here's another version of the joke from the pop television series, The Big Bang.
There's this farmer, and he has these chickens, but they won't lay any eggs. So he calls a physicist to help. The physicist then does some calculations, and he says, I have a solution, but it only works for spherical chickens in a vacuum. Right?
If that doesn't make you laugh, you're probably not a physicist. The point is that in physics, very crude analogies are often used to push science forward. Later in this presentation, we're going to propose the biggest spherical cow in the history of science and ask people to remember that in physics, spherical cows are fair game. Foundational principle number 3 is about symmetry. Symmetry has been a fundamentally important concept in the history of physics. Isaac Newton is famous for having discovered one of the earliest and most fascinating of these, the symmetry between a falling apple and the orbit of the planets. Since then, Emmy Noether's discovery of the relationship between symmetry and conservation laws has become one of the linchpins of modern physics. In keeping with this fact, symmetry is going to play a critical role in our proposed theory of everything. Okay, that covers our 3 foundational principles. Interpretation matters, crude analogies are acceptable in physics, and nature is often symmetrical. Our next step is to describe the main problem in contemporary physics, which is the incompatibility between quantum mechanics and general relativity. This incompatibility springs from the fact that when we try to break the material world down into its component parts, there comes a point when things get very strange. Imagine trying to break a rock down into smaller and smaller rocks until it becomes a tiny pebble. The central mystery of physics is that there comes a point beyond the atomic level when what we see ceases to be a physical thing and becomes a cloud or a wave of probabilities, as if by some strange magic. What the rock is made of now seems to be in many locations and in no location at the same time. Let's get a little more technical. On the left side of the screen, we have the cloud we mentioned previously, technically known as a wave function. It represents what a subatomic particle is before it's observed. The famous Schrödinger equation governs how this wave evolves over time. On the right side of the screen is something known as the Born rule. The Born rule governs the probability that the wave function / cloud will turn into a particle at any given location when we look at it, and the probability is proportional to the square of the magnitude of the particle's wave function at that point. The fact that we can't explain this transition from a cloud to a particle is known as the famous measurement problem. Nobody understands how the subatomic world transitions from Schrödinger's wave of probabilities to the 100% certainty of the Born rule. This empirical reality has given rise to dozens of different interpretations of quantum mechanics, each leading to fundamentally different ideas about the nature of reality. In a recent paper, theoretical physicist Adam Cabello cites 16 mainstream interpretations of quantum theory. The most well-known of these is the Copenhagen interpretation, which simply accepts the so-called collapse of the wave function at face value and asks no deeper questions. It doesn't even attempt to resolve the measurement problem. Another increasingly popular interpretation is known as the many worlds, or Everettian interpretation, named after its original proponent, Hugh Everett. This interpretation sidesteps the measurement problem, but it does so at a very heavy metaphysical price. According to many worlds, we live in only one of a potentially infinite number of other universes where every time a measurement is made, which is to say, every time quantum systems interact, they branch off into different universes. If this interpretation is right, there isn't only one of you or me, but rather an uncountable number of copies of us in an uncountable number of universes, all branching into the future forever. Although this is a mathematically viable resolution to the measurement problem, it makes no intuitive sense and can't be tested. More importantly, it can't be connected in any meaningful way to anything that matters to humans in this world, the one in which we actually live. In sharp contrast to the many worlds, we're now ready for the first pillar of what we believe is a much more satisfying resolution to the measurement problem. It emerges from the two-time interpretation of quantum theory. According to this interpretation, reality is comprised of not one but two wave functions. The first of these evolves from the past to the present, while the second evolves back from the future. The meeting of these two wave functions in the present, according to this interpretation, is what we experience as reality. The research behind the two-time interpretation of quantum mechanics is led by Yakir Aharonov, one of the most innovative and highly regarded physicists in the world. Aharonov has received numerous awards, among them the Wolf Prize and the U.S. Presidential Medal of Science. Over the course of his career, he's made several groundbreaking contributions to quantum theory, among them the Aharonov-Bohm effect and the so-called pre- and post-selection framework associated with weak measurements and weak values. Year in and year out, Aharonov's ideas continue to lead to impressive breakthroughs in many parts of the world and in many areas of physics and math. His recent work on a completely top-down hierarchical structure in quantum mechanics, for example, has promising implications. We'll come back to that in the future. Aharonov's research is not the only body of work that's consistent with the idea that the present is caused by both the past and the future. Other notable contributions have been made by Nobel Prize winners Richard Feynman, who we mentioned previously, and Frank Wilczek. Physicist John Cramer's transactional approach is also interesting, as is the work of philosopher Hugh Price and many others. Hugh Price's treatment of entanglement will be of special significance in a future lecture when we cover an important concept at the cutting edge of string theory, which is the emergence of gravity through something known as entanglement entropy. Maybe the most direct experimental evidence that the future has a causal impact on the present includes the delayed choice quantum eraser experiment. We'll review this experiment as soon as we can in the future. But what in the world does it mean to say that the future has a causal impact on the present? The idea seems completely crazy, but in reality it's not. There's no need to accept the paradoxes of time travel, etc. The idea is actually very simple. When I set out to build a house, for example, I first conceive of the house in my head. I then take steps toward making that house a reality. While I'm working, my conception of a house, which does not yet exist except as a goal, is drawing me toward it and having a causal impact on how the universe evolves. In fact, no matter what changes I make to my goals, the evolution of reality is going to be affected. This is true at the level of everyday experience, and the work of Yakir Aharonov shows that it's also empirically true at the level of particle physics. You as a listener also have a future goal that's causing you to pay attention to this presentation. Your goal, presumably, is to understand our proposed theory. The attainment of that goal is not in the past. You set your goal in the past, and you are presently aware of it, but the attainment of that goal is neither in the past nor the present. Its attainment is in the future, and because of its pull, you continue to listen. Even if you turn away from this presentation, no matter what you do, the future will continue to draw you toward it, at least partly, through your short, medium, and long-term goals. It's worth repeating that what's being described is how reality appears to work at the level of particle physics, where what we do in the future has a demonstrable impact on the present. As we'll see shortly, understanding this is the key to resolving the most puzzling quantum mysteries and the key to developing an intuitive theory of everything. For the empirical evidence, feel free to consult Aharonav's original research or any of our various publications, links to which you'll find in the description. At this point, let's compare the two interpretations of reality we've seen so far. On the left side of the screen, we have the many worlds picture, according to which we're in one of an ever-growing number of universes that continuously branch out every time a quantum measurement is made. On the right side of the screen is the two-time picture of quantum mechanics, according to which there's only one real universe, which is the result of past and future causes. Think of the blue line as the only real universe, which evolves toward the future to some extent according to our short, medium, and long-term goals. Both of these interpretations are perfectly consistent with every experiment that's ever been done, and they're both consistent with the formalism of quantum theory. However, as Richard Feynman pointed out previously, and I quote, "For psychological reasons, and in order to guess new theories, these two things are far from equivalent, because one gives a man different ideas than the other." End quote. The many worlds interpretation leads to an intellectual dead end and says nothing about anything that matters to us in this world. It's also untestable. In sharp contrast, as we'll see shortly, the two-time approach leads to a very intuitive theory of everything that's testable and has important implications for everything that matters to all of us. This is a perfect example of how the same physics and math can lead to a radically different story and to a fundamentally different set of ideas and consequences. That covers the two-state picture of quantum mechanics. We're now ready for the second pillar of our proposed theory of everything, which is string theory. In a nutshell, string theory is the idea that the wave function we saw previously, which represents a particle such as an electron or a quark, is not the smallest building block of reality. According to string theory, if we were able to zoom into the wave function, we would eventually see that it's made up of one or more tiny strings that vibrate in 10 or 11 spatial dimensions. In theory, the mechanics and math of these vibrating strings can be used to derive everything there is to know about the physical world, including the standard model of particle physics and gravity. In fact, gravity naturally emerges from string theory, which is one of the reasons string theory is currently the leading candidate for a theory of quantum gravity and a theory of everything. String theory, however, has several problems. First of all, the energy required to reach the Planck level where strings might be detected requires technology that we're not likely to have for many decades, if ever. A second problem is the fact that string theory requires 10 spatial dimensions, but we can only perceive 4. To make matters worse, some of the most important attributes of string theory are now closely associated with the idea that the universe is holographic. What in the world could it possibly mean to say that we live in a 10-dimensional holographic universe? This sounds worse than science fiction. A further problem with string theory is the fact that the space being used to derive the holographic principle is a negatively curved anti-de Sitter space, which is unlike the universe that we appear to live in. Recent developments in cosmology suggest that we live in a positively curved de Sitter universe. In fact, Just a few months ago, 3 prominent researchers used data from the cosmic microwave background to argue for a positively curved universe at more than 99% confidence level. We'll review their paper and the controversy about the shape of the universe in the future. Even more noteworthy in this regard, however, is the work of Eva Silverstein, who along with colleagues in 2004 proposed a way to convert anti-de Sitter space into de Sitter space. Her goal was to make the holographic principle more applicable to a universe like the one in which we actually live. More recently, in 2018, Silverstein and 2 new colleagues constructed a hologram of de Sitter space, which is more like our universe, by taking 2 anti-de Sitter universes, cutting them, and gluing their boundaries together, so to speak. What you see on a screen is a very crude rendition of what they propose. The impression being given may be cartoon-like, but all of this is accomplished with great technical rigor, and it's fascinating because, as you can see, a spherical ds-ds universe resembles, in a very crude and spherical cow kind of way, the geometry and topology of a human brain. Note especially the parallels between the outer shell and the 2 hemispheres. In fact, we're going to generalize this comparison to ask if there might be a certain symmetry between a ds-ds universe, represented mathematically by the conformal disk on the left side of the screen, and animal brains in general. If this is the case, and there is a symmetry, it makes the concept of holography immediately understandable. The human brain, after all, is unmistakably holographic in how it processes information. Let's take a moment to understand how, but let's first use a balloon to simplify the holographic principle. A balloon has 2 basic parts: its outer surface, which is 2-dimensional, and its interior, which is 3-dimensional. In its simplest form, the holographic principle, which comes to us from black hole thermodynamics and string theory, states that there's an equivalence between the 2-dimensional outer surface of the universe and its 3-dimensional interior. Remember what we said about the legitimate role of crude analogies in physics. This idea suddenly becomes extremely relevant because, in a very rough and spherical cow kind of way, this relationship between a 2-dimensional surface and its 3-dimensional interior resembles the physics and information processing associated with a human head. Making this connection is the key to arriving at an intuitive understanding of a holographic universe. Let's explore how. The brain receives information about the world through the eyes, ears, mouth, nose, and skin. Curiously enough, these 5 sources of information, the 5 senses, numerically match the 5 early versions of string theory that were later brought together as M theory by the famed physicist Ed Witten. We'll save the details of this for a future lecture. For now, let's simply note that when information from the environment travels through our 5 senses and reaches the 2-dimensional shell of our brain, the information causes a series of neurological changes to occur deeper within the brain's 3-dimensional interior. That's precisely what the holography of string theory describes: a 2-dimensional shell, or a quantum field theory, that's equivalent to its 3-dimensional interior. What's even more interesting in the case of humans is the fact that this passing of information from a 2-dimensional shell to its 3-dimensional interior gives rise to the much higher dimensional reality that we experience as persons. How exactly this transition from a 2-dimensional shell to the multidimensional reality of a thinking person takes place is less important than the undeniable empirical fact that the transition takes place. Nobody doubts that information from the exterior physical world hits the 2-dimensional shell of our brain, causing a series of changes to occur deeper within the 3-dimensional interior, which in the end gives rise to the multidimensional psychology within us. On the screen, note the movement of information from the sense experience symbolized on the left through the human brain to the psychology symbolized on the right. This transfer of information from the particles in the environment to the particles that give rise to psychology in our brain gives us an immediately intuitive grasp of how animal brains might share a certain symmetry with the physical and mathematical structure of a holographic universe. Let's back up and reason this out. If string theory is true, again, if it's true, then the rich inner life that we experience as humans necessarily emerges from a physical foundation that has 10 dimensions. What that 10-dimensional foundation is, in and of itself, we can't know because we don't have access to the levels of energy required to probe it. However, just as we can experience the physics and math of a supermassive black hole through our experience of a falling apple here on Earth, the conjecture we're making is that we can experience the physics and math of string theory through our rich and multidimensional experience of psychology. In other words, there appears to be an important symmetry at the heart of string theory, just as there has been at every point in the history of physics. Carl Sagan once famously said that humans are made of star stuff. If string theory and the two-time picture of quantum mechanics are accurate reflections of nature at its deepest level, we appear to be much more than star stuff. We appear to be, in a very literal sense, physically and mathematically symmetrical to the universe. Okay, that covers the second pillar of the edifice we've set out to construct. Let's now drive all of the previous ideas home with a thought experiment. For this experiment, we're going to assume that string theory and the two-time picture of quantum mechanics is correct, and that we have perfect knowledge of brain science. Let's start by imagining a person, let's call him Bob, who's at a fork in the road. And let's pause the universe just prior to Bob making his decision about which way to turn. With the universe and every particle paused, let's zoom into Bob's brain at the three-dimensional neurological level pictured on the screen. At this level of zoom, if we had perfect knowledge of brain science, we'd be able to read Bob's thoughts and emotions. We'd be able to see, for example, Bob's dilemma regarding the fork in the road. For our next step, let's keep the universe frozen and continue to zoom down to the particle physics level within Bob's brain. At this level of zoom, once again, assuming perfect knowledge of brain science, we'd be able to see all of the particle physics states that correspond to the thoughts and emotions that we observed in Bob's brain at the previous level of zoom. Next, let's continue to zoom until we reach the string theoretical level in Bob's brain. At this level of zoom, the mathematics of string theory tells us that we would no longer be able to see things in a classical way. Instead, we would see tiny strings that vibrate in 10 spatial dimensions. At this level of resolution, we'd see that the subatomic particles that were visible at the previous level of zoom actually emerge from this strange hyperspace into which we've entered, and we'd be able to see the long-sought massless spin-2 particle known as the graviton, which quantizes gravity and unifies general relativity with quantum mechanics. For the fourth and final level of analysis, we're going to transfer ourselves to the outer boundary of the universe. We can do this because of the holographic principle, according to which the outer boundary of the universe is equivalent to its 3D interior. From that outer boundary, we're going to be able to see that the strings vibrating in 10 dimensions, which correspond to Bob's experience of the fork in the road, are actually encoded on the two-dimensional surface of the universe. On the edge of the universe, we're also going to have a view out onto what we might alternately referred to as the string theory landscape or multiverse. From that vantage point on the edge of the universe, we have two options. We can peer back into the bulk out of which we have emerged, or we can peer outward toward the collection of all possible branches of the multiverse. Keep in mind that at this point in our experiment, time is still frozen, and Bob has not made his decision about which way to turn at the fork in the road. Remember also that according to the two-time picture of quantum mechanics, Bob's reality is caused by both the past and the future. That means that in order to determine which one of the many possible universes in the multiverse is going to become a reality for Bob, we need to unfreeze the universe and let time evolve. When we do, sure enough, we see from the information on the conformal boundary of the universe that only one of the many possible universes actually collapses into the reality of Bob's world. In this case, let's imagine that it's the universe in which Bob decides to travel to the right. Mathematically speaking, the universe in which Bob lives has transitioned from the Schrödinger equation of many worlds to the one world that corresponds to the Born rule. To verify that the collapse of the Schrödinger wave function that we've witnessed at the boundary of the universe is what has actually taken place in Bob's world, we can test it. We can reverse back through the various levels of resolution through which we've traveled to the boundary of the universe and observe what's happened to Bob. When we do, sure enough, we see that he's decided to travel to the right. Note that we're not making any strange claims about Bob's free will or the nature of his consciousness. We don't need to. For the moment, we're only reporting what we can see and test physically. The preliminary conclusion we can draw is that there appears to be a correspondence between Bob's experience of will on the one hand and the evolution of the universal wave function on the other. As we'll see in future presentations, what's even more interesting is the fact that we can use the same thought experiment to think about entire societies at a fork in the road. When we do, the physics and math of nature are going to come in really handy. Keep in mind that the scenario we've outlined in the previous thought experiment is precisely what all of the empirical evidence associated with the two-time picture of quantum mechanics suggests about the nature of reality, that a future wave function has a causal impact on the evolution of a quantum system. It's important to remember that this interpretation is mathematically equivalent to any and every other mainstream interpretation of quantum mechanics. Unlike any other interpretation, however, it resolves the measurement problem in a way that squares with our intuitive experience of reality, and it has practical implications for everything that matters to humans. It's worth stressing that the movement through the various levels of zoom in our thought experiment is not science fiction or metaphor. It's part of a well-established series of ideas that have been carefully developed over several decades by the world's top physicists, and the entire edifice sits on 500 years of successful scientific development. In addition to the extensive empirical fruit that's been produced by the two-state vector formalism, the original breakthrough paper behind the holographic principle, written by Juan Maldacena in 1997, has become the most highly cited and impactful papers in the history of high-energy physics. From that original work, as we've seen earlier, Eva Silverstein and others have shown that it's plausible to derive a ds-ds universe more like ours. Using similarly rigorous math and logic, physicists Ed Witten and Leonard Susskind have arrived at something known as the ultraviolet-infrared correspondence. On top of that, many string theorists see spacetime emerging from this level of analysis through a promising idea known as entanglement entropy. There is much more to say about all of this, but we'll save it for a future presentation. In the future, as time and resources permit, Our plan is to break phi and psi down further to incorporate a more complete picture of physics into the two-time framework. As you can see on the screen, this includes quantum mechanics, all of the force fields and their corresponding particles, including the Higgs field, and of course quantum gravity, which is going to emerge through entanglement entropy and through the 10 dimensions and holography of string theory. So, the million-euro question, is any of this testable? The short answer is a resounding yes. All you have to do is make a decision about the future and watch how the universe evolves according to your decision. We propose to take this at face value because this is how reality appears to work at both the quantum level and at the everyday level in which we live, independent of whether we have free will or not. We'll take up the question of free will in the future. For more rigorous testing of our proposal, remember that Aharonov's two-state approach has already led to various empirical breakthroughs. It's true that Aharonov's interpretation of quantum physics is not among the most popular, but that's completely understandable because the idea that the future causes the present is a very strange idea. In this presentation, we've attempted to change that by explaining how our goals, in some sense, come back from the future to have an impact on the present. This may seem like a new idea, but in reality it's not. At the dawn of Western civilization, Aristotle identified the impact of the future on the present and named it final causality. The two-state picture and the empirical fruit associated with it appear to vindicate, at the quantum level, Aristotle's common sense ideas about the nature of causality. What about the holography and multiple dimensions of string theory? Can we test for them? This is where the value of our proposal starts to kick in, because it's going to open up many new low-energy ways to test string theory. In addition to the new prospects for testing, remember that in terms of its number of adherents, its impact on other areas of physics and math, its natural ability to quantize gravity, and in terms of its overall coherence and beauty, string theory is, by far, the leading candidate for a theory of everything. In this presentation, we've made the argument for string theory even more compelling by making holography and multiple dimensions understandable. By conjecturing a symmetry between animal brains and the universe, we've been able to offer an intuitive explanation of what it might mean to say that we live in a 10-dimensional holographic universe. To express it as one very beautiful idea, our brains appear to mimic the physical and mathematical structure of the information in the universe. To be clear, we're not arguing that nature thinks and acts like a human, any more than we would argue that supermassive black holes are equivalent to falling apples. The universe obviously exists on an unfathomably larger scale than humans. What we're doing is simply positing the existence of a symmetry between the physics and geometry of animal brains and the physics and geometry of the universe. Understanding how information is processed in the context of this symmetry has important implications not only for physics, but for every other branch of study, and that's the main point. To return to the issue of testing, note that some of the world's top physicists are currently working on various low-energy ways to test string theory. These low-energy options bypass large-scale projects such as the Large Hadron Collider in Geneva. Especially noteworthy is the work of famed physicist Leonard Susskind, who predicts that we'll soon be able to test key concepts in string theory by building brain-like shells using quantum computers. Other noteworthy possibilities are being promoted by people such as Juan Maldacena, Nima Arkani Hamed, Qumran Bafa, Eva Silverstein, Eric Verlin, and many, many others. Still other possibilities can be found in quantum information theory, artificial intelligence, and in fascinating new work being done in brain science using holography at the University of Berkeley. We'll delve deeper into these various potential tests in the future. The most compelling and important way to test our proposed theory, however, is by drawing out its implications for other areas of human activity where the proposal can be tested. This is a fundamentally important idea. No other interpretation of physics even comes close to revealing a concrete social, political, and economic framework designed to safeguard the long-term survival and flourishing of humanity. We'll flesh this claim out and put some mathematical teeth on it in our next lecture. Let's summarize. In this lecture, we started by pointing out the important role that crude analogies, interpretation, and symmetries play in physics. We then used these concepts along with the two-time picture of quantum mechanics and string theory to develop a brief and intuitive theory of everything. We've shown how to understand the two-time picture of quantum mechanics through our subjective experience of goals. We also responded to the three most important objections to string theory by providing an intuitive explanation of multiple dimensions and holography, and by opening up new low-energy ways for testing. From this new perspective, we've been able to conjecture the existence of a symmetry between animal brains and the topological structure of the cosmos, giving rise to the idea that we are, literally, physical and mathematical copies of the universe. We've communicated all of this in a way that is simple, intuitive, and consistent with every experiment that's ever been done. If you're interested in delving into more detail or reviewing the formalism behind our proposal, feel free to consult our book, A Brief and Intuitive Theory of Everything. You'll find links to the book on our website. If you have any questions, feel free to leave a comment or write to us directly. At EISM, our mission is to engage with individuals and organizations of all types. If you'd like us to visit your school or group, or if you'd like to know more about the various seminars and other forms of training we offer, please contact us. We'd love to hear from you.